My name is Ataullah. I'm going to present behavioral biometrics, a new form of identity verification. This is something that I have been doing research on since last 6-7 years. So it would be nice to see how these behavioral biometrics are developed, why there is a need, for example, how to evaluate them, and how they are different from existing approaches. Okay. So just if I summarize the outline, we will say how we are identified. We will start with, for example, even in daily lives, how we are identified. She is Barbara, I am Guriro, he is Dia. We just look at each other, by the face, we identify each other, right? By walking style, we identify each other. By voice, by listening to someone, we identify them. So this is how we are identified, right? Why biometrics? I will talk about this. Why biometrics? Why is it important, and why should we use biometrics for our applications? And then the question, why behavioral biometrics? I will talk some limitations of this biometrics, and then I will propose behavioral biometrics and some behavioral biometric-based solutions that we have developed. For example, I will talk about them. And I will talk about behavioral biometrics for next generation devices. The next generation devices means smart devices to me. Smartwatches, smartphones, tablets, for example. And some innovative solutions. Sorry, I said this innovative, but because they are my solutions, I should not have said this innovative solutions. If you want, for example, I will do some hands-on exercises as well, just to be sure that we are on the same page, how to develop a behavioral biometric solution, for example, for something. And then we will end with just summary and the future work. So, motivation. The question that I asked you earlier, who doesn't own smart device? All of you have smart devices, right? These smart devices, for example, could be smartwatch, could be smartphone, could be tablet. Okay. So if you own these smart devices, you are among the 61% of the entire population who owns this device. So these devices are very popular. These devices are very personal. These devices provide you anytime, anywhere computing. That's why they are extremely popular and they are used everywhere. And it's a study that says by 2025, 72% of all the internet users will solely use smart devices to access the web. So laptops or desktops, they would not be used, at least as per this study, for this internet accessing. These internet resources will be accessed using smart devices. Okay. Now, let's start with tablets. How many of you own tablets? Yes, fine, 5-6 people. Okay. What do you use it for? What do you use your tablet for? Browsing internet, very good. Making movies? Watching movies? No. Studying papers? Yes, studying papers.
Working hours.
Reading lots of papers.
Giving lectures. that is a very good application. Actually, these tablets are used for a variety of applications, like teaching as well. So for playing games, it depends on the age, it depends on the users. Okay. So for me, like for example, I used to play games. I used to read papers. I used to watch movies especially while traveling to Trento or
By car?
And by train, of course. By car, no.
We have seen security problems.
So I'm among these users. 84% of the users, they use tablets to play games. Just some statistics. And searching for information, like Yanis said, 78% they use their tablet to actually search on the internet. So you see, tablets are very, very popular. Okay, and they could be used for anything. right? From shopping online to reading books, consuming entertainments, doing online shopping, talking to your friends, family members, making videos, audios, everything. So they are extremely popular. This is something that we are agreed on. Now, then comes smartphones. This tiny device, for example. This is called smartphone. And they are also very, very popular. Why are they popular? Because they provide anytime, anywhere computing. You have mobile connectivity. You could do whatever you want to do with a laptop or with a computing device. And powerful processors these days, they have powerful processors, long-lasting batteries, and the GPS, Wi-Fi, all these features, they make them very special device for us. So imagine if you have to spend a day without mobile, how would it be looking? It would be difficult. So here there is a point. The point is we use this device in shorter, longer, and frequent sessions. This is point that I want you to remember. Unlike computers, for example, when we enter password, we do like at 1 hour, 30 minutes, 2 hours. Normally, these sessions are very long. No, normally. And then at the end, we just log out and we just go around and take some break. But here on the phone, this phone needs to be accessed in frequent, shorter, and longer sessions, right? All three. Now, a study shows that this phone, for example, we access it every 6.5 minutes. So 150 times a day, we access our phone. And imagine entering password 150 times. Commerce. Now, the result is, what are the consequences of this? Because we have to use all this information, we have to protect everything. This global smartphone users, they are increased by approximately 50% in this period of 5 years. So people, they are actually buying, they are coming, to use these smartphones. And UK is now a smartphone society. Smartphones are very popular in teenagers, actually. So these teenagers, these people, they actually use smartphone as the only computing device. And computer usage falls as 20% of the mobile phones, they go mobile only. So this shows that these devices, they are extremely popular and among every age group, not necessarily in the teens, but every age group, they are extremely popular. And smartwatches, okay? So these smartwatches, we don't just use them, for example, to stay in touch or receive notifications, for example. They are used for plenty of applications, plenty of things. Notifications, we receive notifications. You see, you have a group meeting and sometimes you do this navigation and you do everything you want to, for example. Some advanced users, for example, they use these watches to control their, for example, to control their devices, to control access to their devices and to control access even to the secure infrastructure as well. Fitness, answering calls, and also like I have added here social etiquette, because if you are in a meeting, if I am in front of you, and if I see this phone, for example, it would be a bit rude, to see my phone in front of you, rather than doing this. The purpose is the same, okay? So smartwatches, they are also very, very popular. And all of these devices, they are very, very personal. When I say very, very personal means nobody would like to share these devices with anyone who he doesn't trust. So what are these devices used for? Okay, beyond classical communication, the purpose of these devices were just, for example, to receive calls, to receive messages, to place a call, to talk to someone. This was the classical, cause of these devices, the use of these devices. But now they are being used to take videos, make movies, for example, or take pictures. We use these devices for social networking. Like we use it for Facebook, to access Viber, to have, LinkedIn, WhatsApp, Skype, Twitter, everything is there on our smart devices, on tablets, on phones, on watches. Significant fraction also does online transactions using these devices. Okay, transactions like Google Wallet, for example. This one, you see, you can pay with your watch, for example. No need to take with you additional, your purse, for example, to pay. Or these smart devices, this is the negative point that I want you to focus on. These devices, they continuously track the user's locations. So you don't need any additional spyware, for example, here, no? So they are continuously looking at your location, continuously looking what you have been doing, for example. So they have full control over users' sensitive data, right? And all of these apps generate and store very personal information. It stores, it generates, you enter your PIN, you enter your password, you enter your code, for example, that code needs to be saved. So all of your sensitive data is stored, is generated and stored on that particular device, right? The point is, this data needs to be protected. How? How should we protect this data? First line of defense is authentication, then encryption. Okay. Additionally, this is also another scenario, for example. Users use these devices, for example, to talk to their IoT controller, for example. If you consider a scenario of smart home, for example, okay, you want to execute a command, turn on this button, turn on this air conditioner, for example, using this, right? Or open the garage door for me, right? So these devices are also seen as a medium between, communicating with the real device to execute the command. Here I will simulate a scenario of this building we will discuss. Then another thing is, like I said, for example, they are not just used now for example, for classical communication. They are also used to access cars. Now this Apple, for example, watch is used as a master key, for example, to access your car. So this data that is on your phone, on your watch, for example, this needs to be secured. This needs to be accessed, right? Any question till now? Okay. So here comes the topic, user authentication. I said user authentication is the first line of defense. So if there is a strong mechanism implemented here, you will not be able to see the content inside this phone, right? It should give you like 3 attempts, for example, to enter your secret, and 3 attempts, for example, if you are not providing any secret correctly, what will happen? Your access will be denied, right? So user authentication is the process of verifying the identity of the person. If I'm claiming I'm Guriro, the system should identify me. This system should verify my identity. How this verification is performed, we will see. So being able to prove a user is who she or he claims to be, is authentication. Now, I told you, password was created, this mechanism was created in 1964. By that time, there were no smartphones, there were no smartwatches, there were no smart devices. So mainly the system was built only for laptops, for desktop, for computers, no? So for computers, as I told, in computers, you don't use this computer frequently, okay? Or for short sessions. You use it for longer sessions, 2 hours, 3 hours, and then you log out. So for their password is okay, but on phone, problem. Now, protecting long-term sessions, this was the main core of developing these solutions. One shot, talk-to problem. The decision is boundary. One shot, I mean, either you are accepted or you are rejected. This is the outcome of entering password. If you enter your password correctly, you are authenticated. If you didn't manage to enter correct password, you are denied the access, right? So this outcome is binary. Now, these days, for example, with all these devices, what is required now? The requirement is long, short, and frequent session. Users are our friends. If they are using 150 times their phones, we should have some simple solution that help them, no? Instead of adding passwords every time they need to access the phone. This is one thing. Repeatable, as and when required. So when I say as and when required means this system should be continuous. It should be continuously authenticating me. I'm in the hands of Buriro. I'm in the pocket of Buriro. No need to authenticate him. When it doubts, it should authenticate. It should ask for my secret, for example, or anything. Risk-based and adaptive. This is the need of the day. And continuous. Now, authentication mechanisms. There are 3 mechanisms. One mechanism is password, which we call knowledge-based. Okay, password, entering PIN, password, graphical password, for example. They are knowledge-based schemes. Then we have possession-based, smart card. That card you use to access this building, for example. This token, I call it token as well. This one, sorry. Okay, so, and characteristics-based, physical, behavioral. Gait recognition is behavioral biometrics. Face recognition is physical biometrics. Okay, iris recognition, physical biometrics. So here you see, for example, these are all physical biometric, types of physical biometrics. Fingerprint, hand, iris, this is sclera. This face complete features, DNA, all these are physical biometrics. And behavioral biometrics, keystroke. Anyone knows about keystrokes? Because you implemented this. Anyone else? Keystrokes.
The power that you are pressing on the keys, you can identify.
Close, very close.
The time between shifting from the key.
Perfect. This keystrokes means the time, based on the timing differences. You press the key and you release that key. The difference between those periods, pressing and releasing, and pressing and releasing another key, releasing and releasing another key. These, timings could be used as an invisible layer, for keystroke dynamics. So this keystroke dynamics is already there. Signature recognition is a very, very popular biometric modality. It's a behavioral modality. Have you signed your contract? You signed it, right? So the signing is an acceptable way of, acceptable modality to everyone. So people use this modality also. Voice. Even if we have, we meet someone 10 years later, for example, we will identify him from his voice, for example. It's also a behavioral modality. Now, why? How many of you have passwords on your phones? How many? 5. And biometrics? More users have biometrics. I will go with the flow. So you see, biometrics is a preferred choice. Because for the knowledge-based mechanisms, for example, these passwords could be lost. I told you, an average IT person has to remember 31 passwords. It's very, very difficult to remember passwords, right? So they could be lost, they could be stolen, and because this attack space is very small, for example, you are required to enter 4-digit or 6-digit password. How many different combinations could be to launch a brute force attack, for example? For 4-digit PIN, it should be 10 to the power 4. So just 9999, 10,000 different combinations, no? Matter of seconds. So that's why people that don't use these passwords anymore. This one, graphical passwords, or these tokens, for example, keys, your tokens, your cards, for example, they could be cracked, they could be forgotten, they could be stolen. If you remember these 9/11 attacks, 2 of the attackers, they were using at least 2 stolen passports of Saudi Arabia. So these tokens, they can be stolen and identity could be theft. Then that's why biometrics are preferred because they are unique. You are not required to bring them explicitly. They are with you. They are part of your body. No, they cannot be stolen. They cannot be forgotten. They cannot be shared. So they provide you more security as compared to these passwords, pins, token-based authentication mechanisms. So biometrics is the need of the day. Now, anyone knows about biometrics? How this biometric system works? Biometrics. No? Yes, Yanis? Yeah, these are the modalities. You provide the fingerprint. This data from this fingerprint is extracted in the form of features. Then these features are saved somewhere in the database. And then this database, these features from this database are used to train the classifiers. And then this trained classifier is implemented in real time, right? Then test set comes in and it is tested against that trained classifier. Very good. So, because most of you don't know how biometrics works, I will just very quickly give you a brief overview of it. So, the use of physical or behavioral characteristics, for example, for human beings for automatic identity recognition. So, you see here recognition, face, fingerprint, iris, palm print, gait. This one is behavioral. Voice behavioral, signature behavioral, ear, size of the ear. Okay. This DNA, this palm veins, even these veins could be used to identify people. Hand geometry, sclera, pericular, keystrokes, fingerprints. There are a lot. Okay, so you can develop any biometric system using any of the modality. But before implementing or before developing the solution, make sure that you choose the best modality. Now, here, for example, consider this as a biometric system. Here, which sensors should be used here?
Camera.
Yeah, camera. Yeah, thank you. So you could use camera because it's a face recognition system. So here, you took the image, took the picture of a person, processed it, extracted the features, and these features are saved as templates somewhere in the database. And here is the classifier trained on those features, and then it identifies you whether it was you or someone else. Okay. So this sensor is very important. It varies across different modalities. A detailed biometric system, for example, works this way. So you are here. Here you have mic. You have this whatever sensor you are using. If you are using voice biometrics, you will be using microphone, for example. Or here, mic, for example, then you have here, you collected the signals, you extracted, the data is in the raw format, right? So you pre-processed it, you extracted the features, and this picture vector is stored in this database. So you have created template out of that data. Now, there are two parts of this biometric systems. One part is called enrollment. Another part is called verification. In enrollment part, we say, for example, you know sign up process. Whenever you want to access a service, for example, you first sign up, you provide your details, right? And then you test. So this enrollment is called a sign up, for example. So you must provide these data, for example, more evidences, more data to perform this enrollment, and then for the testing, it will be done with just one attempt at least, or with any number of attempts. An attacker also could apply, could attack also this system. We will see how. Now, enrollment. In enrollment, it is controlled. It is supervised. So, for example, have you ever been to Kastura? Okay. So, for applying your permesso di soggiorno, for example, what are you asked for? 10 fingerprints, right?
And also the
Clapping as well?
these as well.
This
The
palm.
fingerprints and
Palm. Okay, I'm going to suggest them this clapping as well. But okay, this palm is also collected. Now the point is, you see, if you have been there, you will notice that a lady, for example, sitting next to you, actually sometimes say no, put correctly. Sometimes she touches your finger and rolls your finger like this on the sensor. Number one, supervised, controlled. This enrollment is very, very important. It should be controlled, it should be supervised, and as many samples as possible, because you have most of us have 10, so they collect 10 samples. Right? Now, multiple measurements, and they say, while collecting, she also looks at the quality of the data. No, this part is missing. No, we need to do it again. It is also possible, right? So quality control check is performed as well, and selection of the best sample or merging of the best sample also happens. Now, for same way, the features are extracted. So you have 10 samples, you have provided 10 samples, also palm print samples, they are saved some. While in testing, for example, this one, for example, this project is very famous project in biometric community. It requires a lot of time as well. Enrollment. It requires some time, right? Because for fingerprint, you may take like 10 minutes. But if she asks you, okay, you have to sing this song as well, because I need to save this voice script somewhere as well, right? So this way, for example, based on the biometric modality, the time can vary. So for example, this Aadhaar project in India, they probably have already enrolled around very close to 1 billion users now. And this card, they have included all this information in a card, they call it Aadhaar card. And they distribute, ration, they distribute every facility based on that card. So they collect everything, images, iris, for example, 10 fingerprints, palms, everything. And this data is translated to the chip, and the chip is part of it. Verification, because you are not supposed to use, this phone. You are supposed to use this phone anywhere you want to, right? So this now providing a sample, for example, will be identity verification. So if I need to unlock my phone now, what will I do? I need to enter 1, 2, 3, 4 or password or whatever, and then it matches me and grants me access if this password is correct. So this is testing, this is verification, it has to do. This verification is normally not supervised unless this verification is performed at airports. Okay. And reading of the biometric template. Most of the time, this testing is a single test, providing just one time your sample. Process is the same, then this data is matched. Which data is matched? The data that you have extracted, for example. Okay. Now, just giving you an example, matching and decision making, how this data is matched. So you see here, these are, for example, query fingerprint, this is, and these are the extracted features, minutia points, these are called these blue dots, you see. And here in the database, Kastura received your finger, for example, this image, it is already in the database. Now they measure, when you provide this sample, they measure the difference between these two minutia points. Okay, so if this difference is more, for example, it means they are less similar. So if this distance is small, it means they are more similar. So based on the similarity or based on the difference, these are identified. Okay, this identity is verified or identity is confirmed. So here the theory is, main requirement is we need this decision making to be very quick. It should not take longer, for example. Consider giving, let's say, I say, on your phone, enter 16-digit password, which should contain, alphabets, underscores, numerics, characters. Okay, 16-digit long. So you will need to enter 16-digit, it will be difficult. Biometric systems, they are evaluated in the form of false match or false non-match, false accept rate or false reject rate, or we say equal error rate. So false match means an imposter sample matched incorrectly. Okay, this is called false match. False non-match means a genuine sample didn't match the reference template. So I am the genuine user of this phone and my sample was mistakenly misclassified. Okay, then you have equal error rate. So these two errors, they are very important. For sometimes, for usability increasing, for example, for increasing the usability, we don't care this. Sorry, this. We care this. So for example, if I develop a system and it is 70% accurate, what does it mean? If it authenticates you like 4 times out of 5, okay, 1 out of 5 attempt gets rejected, means 80% times you are truly accepted, right? And when another person tries in, if he says, for example, if he tests and he, among the 5 attempts he made, if he is tested positive all the times, what will happen? So you will say, I have higher false acceptance rate, right? But for usability, for example, we can say, we will make this system more usable in a way that it will never reject you. Okay, but we are not saying it will never accept anyone else. You got my point? So this, based on this, some companies, they also suggest using this EER, equal error rate. So they say there should be a trade-off that exists, the security and usability trade-off, and this should be, uniform based on this equal error rate. So sometimes they said it should be equal. Now, also like for graphical representations, for example, we report these results in terms of ROC curves. Anyone knows ROC curves? Receiver operating characteristics curves. They exist in image processing, they exist in computer vision, they exist in everything, everywhere. So you plot these errors between false accept rate and true accept rate of a system. Okay, and based on different thresholds, you compute these curves. So the curves closer to this coordinate is very, very accurate. The curve lower than this coordinate, for example, here is less accurate. Okay, so this is ROC curves. There also exist DET curves. We will see. Now, can anyone tell what is the problem with the existing authentication approaches? Yeah. How many times you would be happily entering your password on your phone? 0? 0. But you will still have your password, right?
And I forget.
Exactly. This is my claim. You forget your passwords. So the point is they are difficult to remember. I mean, this is a problem to the usability. And they are non-transparent, means every time I need to unlock my phone, I need to enter PIN. So they require extra effort, okay, for me to enter my password. So this is against the usability. Shared, forgotten, this poses a security threat. Passwords could be shared, could be forgotten, like I already said. Attack vulnerability. I said there are not like, if you are using 4-digit PIN or 6-digit PIN, the combinations are not many, so it will be a matter of minute to apply a brute force attack. Now, Yanis, don't say you are using 1, 2, 3, 4 as your password.
Yes.
Congratulations. If not, you are not among the 10% population who uses out of 3.4 billion passwords database. You are not among them. Very good. Congratulations. And 6% of them, they use 1111 as password. So you see, 4, 7, 1, 2, 1, 2, 3, 4 zeros. These are the passwords that we use. And for example, graphical passwords like this. It's very simple. Sometimes M, sometimes N, because we do not have, a wider option available. We have only limited option. Now, apart from this, there is also another point that I want to make. When you are interacting with your device, you always leave your smudges on your devices. Touching tablet or touching, for example, your phone or entering your PIN, you leave your smudges, and those smudges could be learned like this, for example. So this is also a problem. Now consider, for example, if these problems, they exist for smartphones, how about using them on smartwatches? It's even more difficult, no? So smartwatches also we have to accommodate somehow. So this study says users consider these passwords, graphical passwords, as annoying and don't use them. 70% of the population, they don't use passwords anymore because they don't trust their passwords anymore. Right? Now, physical biometrics. If you are working in physical biometrics like fingerprint, face, you would be a fan of this, right? You would say these are the most secure biometric modalities ever researched, no? But it's fine, but the application is different, the scenario is different. We are using them on phones, on smartwatches. They are also non-transparent. Whenever you need to unlock your phone, you need to provide your fingerprint and it's unlocked, right? So every time you need to access means transparency is not there, non-transparent. And environmental effects, they also pose some usability. Like, for example, using face recognition in dark, in evening, for example, would not be that accurate as compared to now. Okay, so environmental conditions also, and attack vulnerability as well. Like fingerprint, for example, is considered the most secure biometric modality ever. But this lab from Germany, it's called Chaos Lab, they are continuously hacking Apple Touch device on the second day of their release. And the point is, Apple doesn't learn from these things. So the point is also, apart from this, these are time consuming. Physical biometrics already exist. These two, for example, here there is a fingerprint sensor. Here, this watch uses face technology. This one is Fujisto's device. They use iris recognition, for example. And here, this watch also uses iris recognition technology. So the material is there, but the point is, you take 15 to 20 seconds of your time on this device, even. So because you have to bring your phone in front of you so that, the circles are filled with your eyes and then they catch your sample and, perform this authentication. 15 to 20 seconds. Would you be willing to use this system? 15 to 20 seconds, come on, it's a lot of time. And also, like now, consider using this technology, iris recognition, on this watch. It would be difficult, no? So these problems, apart from those problems, there exist also other problems. Sabri, who is he? Is it Barack Obama or Osama bin Laden?
No, Bin Laden.
Osama bin Laden? No, it's Barack Obama. You see? So the point is, because physical biometrics also, we use, for example, social sites. We leak our data on the internet. Okay, if I search your name, I will find the image of Dia somewhere, right? So the point is, it's very easy to launch an attack, a replay attack, for example. So here, for example, in order to access your computer, you need to print an image and show to your computer, and you will be granted the access. The point is, it's not very difficult to spoof these systems. It's very, very easy. And people are doing this. So all these problems, they actually motivate for better solutions. Have you heard of this story? For example, a researcher, for example, extracted fingerprint from an image of Trump. So Trump did this guy took the image of this fingerprint and he extracted the fingerprint of this. It's possible. So yes, sometimes it was believed that this modality is very, very secure, but now, trust me, 4 out of 5 users, they are hackable. This is a very strong statement, but from the smartwatch scenario, it's doable. So, but it's not a foolproof solutions anymore. Also, in addition to all these phones and everything, in order to access your building or access this room, for example, we are supposed to remember pins 1, 2, 3, 4 if you want to access a secure infrastructure. Okay, so these could be the solutions, digital keypad. They are already there in the market. And also like fingerprint, also, this card that you showed me, and also this device pairing mechanisms. They already exist. But as I showed you, there are a lot of problems, for these systems. So I will address also this scenario as well in my research. Now, I think we are now able to make some conclusions, right? So conclusion is passwords, pins, and physical biometrics. Actually, they do not fit the current interaction model. Okay, for this new landscape. Are you agree? No?
No.
Why?
I think it depends on the context.
I'm talking about smartphones and smartwatches and smart devices only. I'm not talking,
Like even like for instance, you talked about say for instance when you're using your smartwatch, it does not make sense for you to do like this.
Exactly.
But like I could even be talking to you and unlock my phone like this with my thumbprint and it still essentially works. I can basically look at you and be recording or do something.
Very good. Very good.
So that's what I'm saying.
Okay, yeah, fair enough.
Yeah.
Fair enough. I accept this. But in larger context, for example, I'm talking about smartphones, I'm talking about smart devices, tablets, even for example. There is a need for new, acceptable, and secure metaphors. My point is, all these mechanisms, they are developed based on security. They are security-driven systems.
Yeah.
No one cared about usability. This is my point. So user is also your friend, is not a foe. No. So if the system is usable, if security is acceptable, I think it should be better. Right? So then, as I'm saying, newer, acceptable, and secure that are usable, they are required. Design should depend on usability, security, and bring your own device principle. Everyone brings his phone or his watch, for example. So why shouldn't we use that resource to authenticate? In security, humans are considered as the weaker link. Anyone who is disagreed on this? Are you agree that humans are considered as the weakest link in cybersecurity, right? So, but the twist here is, for example, what is unique about a person we use to enhance that security? We are using that particular uniqueness to enhance. So the goal is to design lightweight, user-friendly, and secure authentication and access control mechanisms. This is the need of the day. Now, what is behavior? Sleeping is also a behavior. There is a wide range of actions everyone does. For example, this walking style. This is behavior. My talking style is a behavior, voice recognition, for example. So, unique strategies, different skills, and different strategies when you apply to do something. Okay, they are called behaviors. And these behaviors, mind you, they are not new. They exist somehow in other studies, psychology, for example, in other studies as well. But in this authentication scenario, in this authentication domain, they don't exist. So, the advantage they provide, for example, consider if you have voice recognition. Okay, you don't need any sensor, no, any extra device like fingerprint scanner, for example, right? So it means data could be collected unobtrusively, right? And no need of additional hardware. And arguably very secure. Why I am saying arguably? Because they are not researched at the moment up to the extent they need to be. So it's difficult to draw a conclusion at the moment. Challenges, yes.
Can you go back?
Sure, sure.
So before you said that, for instance, you could log in, grant access to a computer with a picture of the face.
Yeah.
Why can't we just reproduce some voice note of somebody to log in with this voice, or record this person walking and show the video to a camera?
Exactly. This is the threat to behavioral biometrics. Okay. This is right, yeah. The same replay attack, yes, it could happen.
Okay.
Yeah. So the challenges is, first of all, this behavior needs to be unique. The challenge is, when you identify a gesture, for example, I identified this gesture. This is called snapping. So this snapping, for example, is unique from person to person. If you plot, so there exist two types of variations. One is called intra-class variations. The samples, the variation in my samples only, for example, just to give you an example of this lady. So this is intra-class variations. Same person, but different poses, different, So this is called intra-class variation. For inter-class variations means the differences between you and me, between your samples and my samples. So idea was, the challenge is identification of a suitable biometric modality that is unique, that is stable, that is secure, and whose performance is good. So we identified these two behaviors. One, for example, the touch. So touch, for example, the way you write on your phone, for example, is unique. Okay, and it has very low intra-class variations and very high inter-class variations. This is challenge number one. Challenge number two is this behavioral biometrics. They provide you. I would not take it as a challenge, but it's always good. One time, these behavioral biometrics, they always provide you one-shot login. One-shot login means you need to be authenticated at the start of the session. You want to unlock your phone, you need to provide your biometric credential. That's it, at the start. Then this whole session, you are authenticated, right? You remain authenticated. For continuous authentication means even after you unlock your device correctly, but then continuously you are authenticated continuously without even letting you know. Okay, unless this whole session finishes. When this stops, authentication is not required. Different situations, applicability in different situations. Because these fingerprint face, they are static in nature. You could use them while running. You could use them while, in the train, for example. These behaviors, they also need to be, we need to be sure that these behaviors remain constant across applications, no? So, now I'm presenting my paper. This is the work that I did in a collaboration with an agency of NATO, NIAS, hold and sign. Now, just looking at you, if you want, for example, to test this app before we start, it would be nice. Or I just want to introduce you to this solution, and then I want you to test it if you want, for example. It is good. As the name says, this is hold and sign. So it means you have to hold your phone, for example, like this, the way you hold your phone, and then you need to sign. Signing means writing your name, writing something that this phone knows, that you want this phone to know, okay? So I call, this is a bimodal system. Do you know what bimodal system is? Two-factor authentication, exactly. So the motivation of using this handwritten biometric recognition is, for example, because it's widely used modality. We use this signature everywhere, So the process of identifying the author of the given text. Okay, is it your writing? Yes, right? So handwritten signature is a specific instance. wide social and legal acceptance in daily life. We used to sign contracts, we used to sign, everything, and if we are accepting that system. Or indicate physical presence, for example, you need to sign when you enter this building, for example. This is the signature of Barack Obama. So the signature is also left somewhere on the internet. Handwritten biometric recognition systems, they are of two types. One, static biometric systems. They process the images offline. So scanned image is processed. You did the signature, and this image of this signature is processed. Okay. So, and compared with the stored image to authenticate and see the difference between them, right? And in dynamic systems, for example, signature is acquired by stylus. So you have a stylus or your fingerprint you could use, for example. This image is taken and this image is processed. And this authentication is performed in real time. So here in dynamic systems, the features are different. So you see spatial coordinates. For example, you have here a tablet. So the starting point and the ending point, they are different for every person. Then you have spatial coordinates in the y direction. Sorry, it was y here. Then you apply different pressures, for example, based on your age group. Inclination angles, the way you write, for example. So this signature systems, especially static systems, there are at least 3 companies working on this domain. So this is already a well-known modality. Now, what is different for me, for example, what is different is I am using, not fingerprint pressure, sorry. I am using the way you are holding your phone, number 1, as a modality. So when you hold your phone, actually the sensors inside it, they record your movements in 3 directions, X, Y, and Z dimension. Okay, so the point is in XY in 3-dimensional domain, it is very, very difficult it is very, very different from person to person. This sample, this digital signature sample. So this is one modality, holding your phone. Other modality is writing your name. Okay, so for example, here, I have written here my name. Just, I want to share with you this. I'm pausing for like 2-3 minutes here. Could you please test this system? Because this system is already trained on my samples. You have to write exactly that, for example. I'm telling you the algorithm, right? So you need to write this burrito. I'm using this as a mimic attack, as a random attack, for example. So I forgot my phone, you found my phone, and you want to access my phone. So can you try 5 times? So how will you do this? You will write here, yes, please write. Bravo. Next. Not authenticated. Keep trying 5 times, and out of 5, tell me how many times you were correctly misclassified.
The whole thing is taking into account.
Yeah, everything.
So you need to also mimic your wave stand.
Exactly, this is my point. I will talk about this in later. Yeah, 5 times. Real-time demo. Let's say like how many times I got spoofed.
Complete, not.
No, not a single attempt got accepted. Here, please.
Okay.
You need to click this test.
Okay.
And write my name, yes? Name is written here.
So for the first time.
Clear, yes.
It's really hard to mimic it.
Next.
Press next.
Not authenticated, okay.
Not authenticated.
Okay.
Are you hand right or left?
No.
Right.
Yeah, this is a random attack, so you are not supposed to
I don't
know.
know. Maybe I will watch you, like if I want
I will
to
do
add
this
it.
later. I will do this later.
I think.
Pass it, please. Yeah, don't give it to Kevin because he has already tested.
Okay.
This one.
So can I ask a question?
Yeah, please.
So how do you decide the thresholds? Like.
I will talk.
Okay.
This is just the second slide of this.
Yeah. Okay.
Just a sec. Did you manage to get authenticated?
No.
No. No. Okay, next. Yes. I'm excited to see results of Yanis. They are attacking my system, Barbara. They are attacking my system already, yeah. Press this test button, mock, and then you need to write this text. Okay. And press next. No. Special. 5 times, please.
If you are trying to be slow,
Yeah.
so
Of course, you need to write it.
really fast.
Yanis.
Okay.
The position how from this.
It's not that easy.
It's very simple. Boom.
I practiced with my mother for when I asked at high school for but I was called I know that there's plans and I was called
The signal
Never again.
Yes.
How many times did you got accepted? Never. Okay. Yeah, this is actually false acceptance. If any of your attempt gets accepted, it means it's a false acceptance.
Yeah.
Because the model is trained only on my samples. You got my point? Next.
In this context, apart from the imagery itself,
Yeah.
does it also, I believe it's real time, right?
Yeah, it's real time.
So does it also include keystrokes? Does it have key?
Exactly.
You were making me distracted for that, but I know this.
Then it's also the position of the phone.
Maybe.
Even I tried very fast, it didn't work.
If you're too fast, if you're too slow, it's also going.
Yeah.
You have to mimic 2 invisible layers.
Even if like you are considering like the way you move,
Exactly.
this is one. Also the speed,
Exactly.
writing, and the accuracy of
There's
writing.
also, I think there's also like inclination of
Exactly. Everything.
I think he is using a fake app that always.
I said the same thing.
No, very good observation. Very, very good observation. No, very good observation. I will do it in front of you.
Or maybe he is just collecting our signature.
Also.
Oh, you're right, that's better. I remember that I have there.
So now you should be able to know what is a random attack. Someone sometimes forget his phone, forget his watch, for example, somewhere, and he. Thank you so much. So just to,
To me, you have like the message not authenticated for all, even though you.
For all of them, you are not alone.
Even though you did it.
He's authenticated.
So,
You did it?
because this model is trained on
Can I
my.
see your signature when you do it?
Sure.
Just want to see it with
Sure.
you.
Look at the speed he's
Can I see
running.
this video before you go?
Part of the factors.
Well, it's not the same.
But we were very slow.
To very slow,
It's
very
the same,
close.
right? But it's still catching the right?
Yeah.
But then it's catching your face.
You have been right? No, so now you are agree that no, this is not a fake ad, right? Okay, very good. Now the point is,
It was different. It was different.
sure, I'm talking about. Now the point is, you should read this. It is a bimodal system. What is it taking into account? Number one, touch points, not a signature image. It is taking into account the touch point passed while signing. So from a particular X point on XY coordinate and to the end, it captures those touch points where you moved your finger. Number one. This is one modality. Second modality is phone. You have not seen me the training, how I train the system. Maybe I trained it in a standing position. And you all tried in sitting. That's why I'm saying it's unique. Right? Now, we have simulated now the random attack. Now I'm signing in front of you. And I can do it as many times as you would like. But still you won't be able to break it. Who accepts this challenge?
I think you use like a fingerprint or something.
No. Just the process. That's the way of writing.
We want to see the source code.
Yes, I want to see that for
Sure.
And the library you use.
For sure. Why not? Java. Sure. We will. Now, challenge? The challenge
will do
now you can,
exactly.
I will do like in front of you as many times as you would like to see. And then you have to mimic me.
Okay.
Right? Okay. You will keep sitting?
No, we'll stand.
Come. Just to be sure. Okay, so this test.
Over the height.
See.
Is it possible to turn the camera
See.
on the phone?
Okay?
Yeah, maybe
I'm authenticated.
so the online guys can see
Here
that.
as well.
Sorry, just a second.
Good, so you go there.
This is false reset. Okay? Okay. Yeah, we should do
If you can, so the online. This is the max that it goes down.
I think we should go here.
Dia, how to do it online?
No, I'm saying can I face down?
No,
This camera.
I think it's not needed.
Because it can go to the back and
it can go to the
to
back like this.
Yeah.
It's
Okay.
It's not official.
Maybe they stand on the table then.
Yes. Okay. You are a good observer. Not official. Okay. Off you go. One.
Make sure to use the same speed as he.
Yes, exactly. This is the point.
And also the
That's
height.
why I'm saying these are unique from person to person.
Yeah.
These are very, very specific. They depend on the size, on the height, on the arm length, everything.
This is then similar to the keystrokes.
Exactly.
Everyone has a different typing speed.
Exactly.
And then it varies.
Exactly. The same concept. No? You accept the challenge? Okay. I will share with you the source code. If anyone wants to work on this with me, I would love to. So this is a hold and sign bimodal system. You saw sign and the way you actually hold your phone. It's a bimodal system, and while having your phone in your hand, for example, they are different positions because of these differences in accelerometer, XYZ, and gyroscopic XYZ tuples, you are not authenticated. So the claim here is we don't need any extra. Yes, please.
Question based on
Yes,
the
please.
Jared. So if you train the model, let's say for instance, while standing, does it mean when you want to unlock, you also have to be standing?
Okay, very good question. I would talk this anyway, I will tell you this. But the point is, this is a very, very good question. So will this mechanism is usable across multiple activities? This is your question, right? Yeah. Yes, provided that you train this system in multiple positions. So the main claim is this system doesn't require any additional specific hardware, right? So the accelerometer and gyroscope, they are sufficient. And we use existing hardware technology. The data collection for this paper, you could read this paper, it's already published. We managed to attract 30 users for this study, and we collected 30 samples in each activity: sitting, standing, and in walking. Walking in the corridor, in the controlled environment. Now, participants were like 22 male, all of them, they were master students or PhD students, and we used Google Nexus 5 for data collection. So, anomaly detection. Anyone who has background of machine learning? Very good. So, one class classification and binary class classification, what is the difference? Can I model this smartphone authentication problem as a binary class or multi-class classification problem? Can I model this? Yes. Why? Would you like to share your samples with me so that I train my model here as well on your samples? No, it's a privacy concern. So specifically for smartphones, for example, smartphone authentication, smartwatch authentication, this problem is one class classification problem. What is the difference between one class classification and binary class classification? Anyone? What is the difference between? So for binary class classification, you need to have the data, the training data, for at least 2 classes. Right, to train the model. For one class or this anomaly detection approach, you have the data from a positive class and you have to train your system only on that class. So this approach is more usable and more realistic. I mean, from smartwatch user authentication scenario. Now, for example, so we used these 4 classifiers initially. We used k-nearest neighbor, multi-layer perceptron, BaseNet, and random forest as initial because they were found very useful in the recent studies, so we used them. And with initial experiments, for example, this MLP classifier, this is called artificial neural network, you call it, or you call it multi-layer perceptron. It worked very, very well, and we were able to get 79% true accept rate. What is this true accept rate? It means how many times it authenticated me correctly. Training on my data and testing on my data. And FAR was just 0.1%. So this is already a very, very good result. But the question is, users should not be buying this solution because they would say every 5th attempt is strongly rejected. Right? False acceptance rate is very, very nice. So every 1 out of 100 attempts will get accepted. This is a very, very good result. But from the usability perspective, user would say no. Rejected, every 5th attempt is not a solution. I would not buy it. So what we did, for example, we thought that probably, features are redundant. The features are not useful, for example. Let's get rid of those productive features and see how much accuracy increases. So we applied this recursive feature elimination method. We applied other techniques as well, but none of them worked well. This RFE method, it worked well. On the training data only, we applied scikit-learn with 10-fold cross-validation. You see, for sitting, standing, and walking, here, for example, with just 10 or 11 features, we already received the highest accuracy. So these 10, 11, and 11 features from these different standing, sitting, and walking postures, we took them and we trained the classifiers on them. So the result says, for example, interactivity. So this is across different applications, different activities, sitting, standing, walking. And here you see, for example, on the full features and on the recursive feature elimination features. So you see, these are intra-class. Okay, so it means, for example, in sitting, if you train the model in sitting and tested it on standing and walking, the result would be worst. For full features especially, they were worst. For recursive feature elimination method, at least we were reaching 60%. For standing also, exactly like this, right? So what was the idea? Idea was to fuse these modalities, these postures, for example. So sitting, standing, and walking, introduce a combined training system where you use fused methodology, for example, for this, and then you test the system. So with this approach, for example, we reach this 94.8% true accept rate. So this false reject rate is just 1 minus this. So 5.2 false accept rate from 0.1, it increased to 3.1, which is also acceptable. And 69.9%, 96.9% was the true reject. So these are very, very good results. So now, for example, we were sure that these results can be solved. Apart from this, what other thing we did, for example, we compared our technique, this technique, for example, with other existing state of the art. So, entering 4-digit PIN, how long do you take? On average?
3 seconds.
Yes, you could be fast. 3 seconds, yes. So from like up to 4 seconds, right? Here, 3.7 is the average. Very good. So the point is, 3 to 4 seconds is very, very common. For biometric modality wise, for example, it's 5.15 seconds. So we compared with this sample acquisition time as well. How long a user has to, provide the sample maximum time. Hold and sign, was the best one, which on average with just 3.5 seconds of data. Then, for example, we tested. We compare them on the basis of testing time as well. How? Because this application is meant for the phone, and you have seen the results on the phone. It means how long this classifier takes to decide whether you are Buriro or not Buriro. Decision time. So this decision time, on average, based on 30 users, it was between this 0.215 seconds to 0.250 seconds. Very, very quick. Because of this MLP classifier. Then we also checked performance comparison, okay, in terms of power, for example. So we applied a standard methodology that is already used in the literature. We used the same methodology, and we used this triple, profiler to profile this power during the process. And, actually, for the 35 attempts, it was consuming approximately what? This one. And if you compare it with 1 minute of phone call, it is lower. So it's a power-friendly system. For 1 minute of call, 1054 milliwatts are burnt. Then, from usability perspective, we say, if you don't want to provide more samples for training, if you are happy with providing just 15 samples, just 15, okay, then with 3.5 seconds of data, you take maximum 65 seconds to provide me 15 samples. And with this data size, 15 seconds of data, you are already reaching like up to 65-66% accuracy, true acceptance rate. This is true acceptance rate. And with 45 samples, this model is now trained on 45 samples. So with 45 samples, you take like 4 minutes to train this system, right? And with 4 minutes of your effort, if it is giving you 93.4% accuracy, it would be good. So usability is also important for us, and other parameters are also. Last thing that the participants who participated to this experiments, we did this usability experiment as well. So this usability standard is called SUS, Software Usability Scale, and we asked users, for example, to rate our application. So it is a 10 questions based questionnaire where you ask users, for example, about their experience with the system. And we got this 68.3% score, which means 72% is considered good. So a bit lower than the good, but it's, I mean, it wasn't. They were initial results, so it should be okay. Right? Any questions? So open issues that we are interested to, you know, to solve, for example, number of testers, because here the number of testers were just 30. You know, in order to draw a concrete conclusion, for example, 30 users are a bit limited, no? So idea is to extend this number of users. For example, if we could 200, 1000, for example, and run these tests not just in the controlled environment, in the wild. You are on the mountain, you need to be authenticated. You are in the sea, for example, you are on the beach. So different contexts, different environments, different locations, a system should be resilient. Training time without compromising too much security. Training time is very, very important because this classifier based on different number of samples takes some time. Also, although this is just a one-time effort for the classifier on the phone, but still it takes some time. Unplanned situations, sometimes you need to run, sometimes you need to face emergency situations, for example, where you need to call someone, you know. So it should cover also those unplanned situations as well. Robustness to multiple attacks. So here we tested this mimic attack and this random attacks. And trust me, none of the attempt, also with those 30 users, got accepted. So which proves that the system is very, very good. And variability depending on iOS, this needs to be, see, because we tested it only on, you know, this, because we collected the data only on Google Nexus 5. But now it's the latest phone, and I don't see any difference. So, I mean, it should not be a vendor-specific solution. It should be a general solution. Any more questions? I would love to see if someone of you tries to train, for example, by himself and test by himself. You can try. Another application is accessing the secure facility. So the idea to use this mechanism works this way, for example. If we need to access this building, like here, for example, at Unibis Faculty of Computer Science, we are required to bring our card, this token, for example, to access this building. Now, the point is, when you reach the building, you can clip only for 2 seconds. This data collected from the smartwatch sensors is sent via mobile network, of course, encrypted to the server that is inside this building. It requires only like 2 seconds of your data, and then it takes 1 second, within 1 second, it authenticates, it decides whether this data that it has collected is coming from the legitimate person. So once you are authenticated, this decision is sent to you on your watch. You are authenticated, number one, and to the door that this person should be allowed to enter. So this is how this system is going to work in order to access the secure facility. The claim is this system also doesn't require any additional hardware. Hardware is the same, accelerometer and the gyroscope. They are sufficient enough for us. So the proposed scheme authenticates users based on the analysis of the captured arm movements you make while claiming. So approach, for example, you see here, you have a watch here. Probably this watch needs to be worn in your natural hand. So if you are right-hander, this watch should be in your right hand. If you are left-hander, it should be in your right. So you did this gesture, for example. This data, for example, it's captured using the accelerometer and gyroscope and sensors. Then you do here feature extraction from accelerometer, from gyroscope. Okay, you extracted those features, those statistic features: mean, median, standard deviation, kurtosis, cosine similarity between two vectors, absolute difference between two vectors. These are the simple statistical features that we have. So you extract the features from accelerometer and gyroscope, and then those features you concatenated them at feature fusion level, for example. So you concatenated accelerometer and gyroscope features, and then you applied feature selection here. Because 60 features, 30 features I was extracting from accelerometer, 30 from gyroscope, all of them 60. So when I, for example, if the same accuracy I can get with 10 features, it's computationally less expensive, right? So idea is to remove those redundant features, which could be done in this module, and then the template formation with those selected features you save here and in the database, and here again, then for example, you do the matching. So this green line shows you the training way procedure, and this red line shows you the testing case, right? So for this experiments, you are required, for example, to do this enrollment supervised manner just for 300 seconds of data and 3 different actions, okay? 3 different body postures. Then you will be able to test it. So for this data set initially, if I could show you the data set also. So this, for example, we downloaded the data. We started from here actually. This is the main starting point. So this Wisdom smartphone and smartwatch activity biometric data set contains data set of 18 different activities. I saw this clapping also here. But the point was this clapping has till now has been used for gesture recognition purposes, not for authentication purposes mainly. Okay, so idea is here is to use those clapping gestures, for example, to see if we can authenticate users based on this. So yeah, so here, for example, they had 51 users. I downloaded the data from there. Sensory readings at 20 hertz. This was the frequency. 20 hertz, 20 samples per second, you could say. 18 activities in sitting, standing, walking, running, and while drinking the soup, they have collected context level data. Clapping, raw, and they have shared with us, the raw data as well as their transform data. So they have also performed this feature extraction process by themselves and have shared this data with us as ARFF files. Okay, these ARFF files, they are attributes, like something, they are actually used for VECA, training and testing in VECA toolbox. So if you see here, for example, these are the feature lists and these are the activity codes. They are from A to R. Okay, so this one, 18 activities. So one of the activities that is R probably we use for clapping. And the features are simple, X, Y, Z tuples. Okay, then you average, you compute the mean of X, mean of Y, mean of Z, standard deviation, okay, and absolute difference, variance, standard deviation, these are statistical features they have already used. Now, authentication here, for example, if you remember, for device unlocking, because this decision needs to be made on the smartwatch, right? So for device unlocking, we are using one class classification. Because the classifier needs to be trained only on the user's data, only this owner or the legitimate user. So we use this Gaussian distribution density classifier, this artificial neural network, which is MLP, autoencoder, for example, KNN, simple k-nearest neighbor classifier. And for accessing secure facility, because this building, for example, has to accommodate, let's say, 50 persons, 100 persons maybe, right? So this is a multi-class classification problem. So here the server, the classifier that is residing on the server has to be trained on the data of all the persons who could actually access this building, right? And then when the testing comes, during the testing process, you will provide a unique ID. You will claim that you are Buriro, right? And this server has to perform this one-to-one match. This query sample with the samples of Buriro only because he is claiming to be Buriro, right? And this way it has to return me my identity. So this is a n-class classification problem. Now, because this activity, this clapping data, it was collected only for 3 minutes. And the frequency was you saw 20 samples per second. So you see, we had only 3,600 values. So out of those values, for example, we had to get only 18 samples per user. Very limited data, right? But good enough to start more analysis, right? So here, for example, training on first 50 samples. This is also another contribution that I want to say here. People normally also perform cross-validation here. Okay, and upon cross-validation, you know, most of the time the results of cross-validation, they are higher normally. So the point is, it's technically fine, but from smartphone authentication scenario, this is not realistic because initial samples, for example, they are not balanced enough. So initial 5 or 10 samples, it's very difficult to, you know, to get authenticated because they are very, very different unless your behavior becomes stable. Right? So here, for example, this setting gives you more realistic scenario, more realistic scenario. So I'm training the classifier on first unstable samples, 9 of them, 50% of them, and 4 for validation. Why I use validation? Because I had to perform this feature selection, okay, and I didn't want to use the test data to perform this feature selection. So this test data remains unseen by the classifier for all the decisions. At the end, when I'm 100% sure of the features, of the parameters, then I use this testing data to get a final testing accuracy. And train and test remains the same for both scenarios. Train set and test set remains the same, okay? So for multi-class classification scenario, for example, 9 multiplied by 50, 450 samples were used for training, right? And testing also, like, if you multiply this, 5 multiplied by, for example, 9, 5 multiplied by 50, 250 samples were used for testing. So, without any parameter optimization, without any feature selection, these are the results. For one class classification, this classifier, Gaussian density classifier, it was giving us only 50% accuracy. It was not that accurate. But with ANN, artificial neural network, simple artificial neural network, we were able to get 70.8%. This is accuracy, not true acceptance rate, not false acceptance rate, okay? So, KNN is 76, but for N-class classification, we were already reaching somehow 90.7, which is already very, very good based on the number of samples of training, 9, only 9 per user. So, feature selection, here in this process, for example, I didn't use any already implemented technique. So here what I do, I did it manually. I call it sequential forward feature selection scheme. So how it works, what I do, for example, I have all these 3 classifiers. I have this training data of all the users. What I do, for example, I find individually the best performing feature. So for example, I train one by one. There were like 60 features, for example. I train each classifier on each individual feature. Training and testing remains the same, okay? And I find the best classifier, best feature, for example. For example, here, let's say, with just one feature, okay, here, the GTD accuracy was like more than 80%, with just one feature. And for this red line here, for example, this one is ANN, it was like 78 point something, and for KNN, it was here. Now, you were able to find the best feature, which is very, very accurate, and then you have to find the next best feature. Not individual, but in terms of 2s, in terms of 3s, in terms of 4s. So this one is the best first feature. Then let me find the best second feature. And I combine 2 features together and see the accuracy, if it increases or not. So idea is to see how long this accuracy improves and at what point it drops. So with this, for example, approach, this GTD, with just first 2 features, it already reached this highest accuracy of 85-86%. And for KNN, it kept on increasing. It kept on increasing like 25, 26 features. So I had to stop at 27 features because it started to drop. So here, for example, you see here for these 2 classifiers, these 2 blue lines, for example, these 2 features, they performed very well. Accelerometer cosine similarity between X and Y vectors and accelerometer's average mean of this X vector. So for N-class classification approach, I use this CFS subset evaluator. This is a standard approach in Weka for multi-class classification. I use this. Now the question is the results, for example, on the selected features, different selected features for one class and for n class classification problem. You see here ANN yielded 63.27 accuracy, true accept rate, and here false accept rate is 7.06. I have not included here false reject rate and true reject rate because they could be computed from 1 minus. If you want to compute false reject rate, you can minus 100 minus 63, 70, 37, just to avoid any redundancy. Okay, so I wanted to show you here this true accept rate and false accept rate, and this is the accuracy. Okay, so if you compare them in terms of accuracy, KNN is better. If you compare them in terms of true accept rate, KNN is better, but KNN has more false accept rate as well. Okay, so this is one, and there is a significant difference between them. So I had to compromise on something, because the true accept rate is higher. I went after. For n class classification problem, you see here KNN, it reached 96.5%. It's already a good start. So KNN had only 0.22% false accept rate. What does this mean? So it means like less than, for example, every 100th attempt, less than a could get falsely accepted. So these are actually very, very good results. Now the point is 50 users, just 18 samples, training samples, someone can doubt. So these results could be biased. So again, just to check the scalability. What do I mean by scalability? It means probably if after some time 10 more users comes in, 20 more users comes in, what will happen? So what we did, for example, we divided these data sets into 10 random users, 20 random users, 30 random users, 40 random users, just to see, for example, if these results vary. Okay, so normally for limited number of users, the accuracy is higher. When the number of users increase, the accuracy drops. Normally in multi-class classification scenario, this happens. But for our analysis, for example, luckily the accuracy remains very, very close. So it's perfectly fine. So it's the system, this solution is scalable as well. Even if you keep increasing number of users, this system will ensure to authenticate very, very effectively. Now, this this process that the experiments that I conducted, they were conducted on a limited data set, 3 minutes of activity collected by someone else. I didn't know how they collected. It is not clear very much. So it's not good to draw a conclusion. I didn't even submit this paper, even if the results are good. So what I'm considering to do, for example, I am considering to collect the data again, okay, on my own terms and conditions. For example, 2 seconds, because these samples, they were computed after 10 seconds each. And 10 seconds, I cannot ask you to keep clapping to 10 seconds to authenticate your watch, no? So this time we have to be, yes, Johannes, we have to reduce this time, just 2 seconds is acceptable, 3 seconds is acceptable. So this is the application that we have managed to develop with my student here. And here you see, it replicates the exact scenario. So you have to first sign up for some service, for example. The sign up requires you to do this clapping for 300 seconds. Not all together, but 100 seconds in sitting, 100 seconds standing, 100 seconds in walking. Then what we do, for example, we have divided this. So what I have done, he is also doing this. What I have done is I will show you also practically how it works. So what I have done is I have, after 2 seconds of data, I have sampled this data. I have generated 50 samples, for example, from sitting, 50 from standing, 50 from walking. So altogether, I have 150 samples, let's say. Here, from 150 samples, what I do, I take first 75 as training, next 25 as validation, then last 50 as testing. This is how it works. For n-class classification, I will show you also, based on the data he has already managed to collect. He has already managed to collect data of 13 users, but in order to draw a concrete conclusion, we are expecting actually to have at least 30 users. So So on 13 users of data, most of the classifiers, they are giving me more than 95% accuracy. Would you believe that? So this actually makes us curious to collect more data and see if this data is biased to some factor or some reason, for example. I would request you all to participate to this experiment. Now, this is our ongoing work. So still, it's a proof of the concept. It's an ongoing work. We are actually planning to, finalize this proof of the concept application, and based on our findings, this was just one experiment. Now he is doing another experiment. Okay, then we will develop a concrete final application based on our finding, which classifier worked well, which features were worked well, which time window was good, 2 seconds, 3 seconds, 4 seconds. And then we will test it in real time, and we will see security analysis, performance analysis, usability analysis. Then we will start writing this paper. Okay. Any question? No? Any question? Anyone wants to see the demo? Is the demo ready? Yes. Is it ready?
Yes, it's ready.
Okay. You can simulate the scenario there. For example, you could sit there. You can collect data, whoever comes to you, for example. So in the meantime, for example, yes.
Should we wait?
Okay, we can wait. We can collect data at that. So, if there is no question at all till now, I would like to show you some hands-on. How this clapping I did. Please correct me if I'm wrong. I'm showing you my source code. I'm not hiding anything from it. Okay. So, no question. Okay. So for this analysis, for example, we could exploit Python, we could exploit Java, we could exploit Matlab, we could exploit Weka, whatever you would like to. But for Matlab, for example, because they have a dedicated toolbox for one class classification, I have preferred this Matlab. So you need to install, if you have Matlab installed, you have to have these two tools, PR tools, this pattern recognition tool, and DD tool. Okay, so just to show you, for example, what is this PR tool? 30, you could download this from here. 37 steps. This one. It's a well-known toolbox developed by the researchers from TU Delft. So for novelty detection in Matlab, they use it. Now, for example, just a refresher. I'm not saying you don't know about this, but just a refresher. So the data looks like this, right? So you have rows, you have columns. Rows means you have observations. Columns, you have features, right? So, and the last column or the first column could be your labels, the true labels, right? So this one, for example, or this two is your label. Okay, here. Okay, so for example, could you see this code? So here, this gen.b, you just have to download these two tools and you just have to set path. You have to just show this path to your Matlab, that's it. Now, for example, if you run this, so what does this mean? Means generate data of 100 points each for two classes, A and B, and divide this data into two sets. This is how this classification is done. So when we run it, we have this A, okay, and now in order to, we have like two classes here, A and B, which have 100 samples each, but it's just two-dimensional data, just to show you how it was. So I'm dividing this into training and testing, because this 0.5, for example, okay, yeah, 50% of it I'm using it for training, 50% of it I'm using it testing. So means training will have 100 samples total from 50 users from A, 50 samples from B. Test also 50 samples from A, 50 samples from B. So you divide this, for example, and
Just a quick, view how it looks like. So your data should look like this. Is it? You are able to see it, Kevin? Okay. So you see here, we have some samples from this red color and some from blue. Now, my question from you is, which classifier do you think would be good for this? Because normally we cannot try blindly any classifier that we have. What we do, for example, we see the data, how it looks like, which classifier is going to work well on this, right? So, just looking at this data, what do you think, which classifier is going to work? Work well, of course. Kevin, which classifier do you think should be good here? This one. Yeah. These red, for example, these blue. You have to say, because if you are training a binary classifier here, this binary classifier's job will be just to differentiate between the two classes, create a line, a boundary between these two, just to separate these two classes, right? Yes. So here, which binary classifier do you think, if we need to separate these two classifiers, is more useful, will be more useful?
For virtual machine.
Bravo, why? Why?
Because you can delimit.
Very good point. So the point is, if you classify these classifiers, they are mainly classified in two parts. One, you can classify them based on their linearity. So most of the classifiers, they are linear in nature. Okay, and others non-linear classifier, because the data is non-linear. Because the data is non-linear, it's not easily separable. We have to use some complex classifier. Very good. So now, for example, just to show you an example, if I use here a linear classifier, you could find these classifiers in their manual as well. I will share with you as well. So, for example, this LDC, what is this LDC? Linear discriminant classifier. Fisher is also a classifier. Then logistic regression is a classifier. Support vector machines with linear kernel, they are linear classifiers. I trained them. I trained also non-linear classifiers as well. And now I'm training. Here I defined them, and now I'm training. I'm training all the classifiers, let's see. So they are, if you have noted, I'm training them only on the train set. This TRN means training set, right? So they are trained only on the train set. And now, just to show you, for example, if I plot a decision boundary for this linear classifier, LDC, this looks like this separation, this classifier boundary is a linear one, right? Now you see here, some of the samples from this red, for example, they are falsely classified as blue, this one especially. And these red ones also, they are falsely classified, right? So you can compute false accept rate, false reject rate exactly the way we have discussed. So you take a positive class, let's say for example, I'm taking this red class. These samples from this red class, how many samples are rejected? So means how many samples of red class are in the blue side? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, probably 12. So this is false rejection of this red line, red class, okay? And false acceptance is this 1, 2, 3, 4, 5. Right? Clear? Yes. Any question? Okay, so if we try, I close this. I try another classifier, for example, with Blake line, plot C, second 2, this one is the other classifier. Again, very similar. So maybe 1 or 2 will false reject rate or false accept rate will be decreased a bit, but overall, this is not going to, these linear classifiers are not going to solve this problem, trust me. So what we are supposed to do, if you just see all of them, they are similar. So you see all of them, yes, okay.
Okay, so like,
Linear classifier is not going to solve it.
okay, that's exactly my question, but is that not, like, do we need to run it to tell? Because visually you can tell that a linear classifier may not even...
Exactly, I could tell, but it would be better if we compute also the error rates, just to see. It will add a lot of value to your observation. So, for example, when we are applying the non-linear classifier, so this first classifier that we have is QDC, quadratic discriminant analysis. It works somehow like this. It's not a linear classifier, so it has drawn a boundary, but this boundary is not good enough. Okay, so then, for example, other classifier we have is KNN. Yeah, here, for example. Now, we should be able to see two classifiers. You see how good is this KNN? This black line, sorry. So you see, now count the false rejection of this red class for this KNN classifier. Just one. Only this, right? And for false acceptance, there are 1, 2, only, 3, this one, 3. So only 3. That's why this is a good classifier for us. But if we keep doing it for, yes?
That good classifier is very specific to the data though. So maybe you have a problem with the generalization.
Yeah, again, the classifiers are supposed to be, they are data driven actually. So they are depending on the data.
So maybe is that one of the problems with finding the classifier is that you have very peculiar, like the one you have just, the one with a...
Exactly. It depends. No. It depends, Dr. Esa. It depends which type of data you have. If this data is linearly separable, there is no need to use advanced, complex classifier. If this data is not linearly separable, you need to have, somehow.
Oh, yes, I agree. But the one, I don't know how, I didn't see how you plot the
Sorry.
The one non-linear one. It seems to me,
this
if you
one.
look at there, it's very, very peculiar to the data.
Yes, you are right. KNN classifier, normally it remembers things that, okay, I have a neighbor here, I have a neighbor here. It's not a good learner, I know.
Okay, so that was the...
It does overfitting, yes. Yes, it does overfitting.
Isn't there a risk of overfitting?
Sorry?
That's the question, right?
Yeah, this classifier does this overfitting. You are right.
So the big problem is that many other classifiers are like projection of the linear. So for example, the supervised machine are projection with a nonlinear function of a linear classifier.
Yeah.
And so these might be representing very well the classification or not. This one really is it's very, very peculiar. And one of the problems we have is certainly to balance, to trade off between finding one or finding the one that is not too overfitting. So it's like reusable so generalizable.
This classifier is doing overfitting, 100%.
Yeah,
I can prove it. I can prove it. But that's why, for example, the other classifiers like random forest, like tree classifiers, they are better at this. They are good at this. So, for example, if you see tree classifier, if it's readable, or I should run it again. This tree is a very, very good classifier, or random forest, for example. So if I run this, and just this R, this is good classifier, but it still has some. If you take this positive class as reference, this red one, for example, it still has higher false reject rate and higher false accept rate, but it's a good learner. It is learning. KNN is not learning. It's just memorizing. Okay, he's my neighbor. He's my neighbor. He's my neighbor. So this is training we are doing only on the train set. You can compare it now on the testing if you want.
But also in this case, would be, okay, it does separate classes, but it's not continuous. So in the sense that you have two disconnected, let's say, lines that for the classifier, which in some sense is not really wanted, right?
Yeah, these are rule-based classification. In rule-based classification, madam, you can have multiple boundaries.
Yeah, yes.
Yeah. Yeah. So this is how these binary classifiers they work. They have just to separate between the two classes, okay, based on their function that they are using, linear or non-linear, for example, or rule-based or quadratic, It depends. When we select classifiers, we always visualize the data, how this data looks like. We plot different scatter plots and see, for example, how the data looks like. If the data is already linearly separable, there is no need to use these advanced classifiers. If not, then yes, you need to think. Okay, so now, for example, I close this. The classifiers are trained. Now you need to compute the errors. Training error, or apparent error, for example. Now, if you see, the training error of this k-NN classifier will be really close to 0. You will see, because you have seen it overfitting now. So, and now I'm computing this classification error on testing. 8 classifiers we are using. And now you should be able to see here. The training error of LDC is 20%. And for KNN, 3C is 0, and RBSVC, this is radial based support vector machine. It's 0.08, 0.08. No, KNN is 0.08, not 0 exactly. Because there were 3 samples. So now, for example, what we do, we also print the labels, the training labels, for example. We got these training labels from the training set, and now we estimate which classifier, for example, performed well. Tree classifier, you see, it has 0.00, this one. Yeah, 0.00 training error. So I want to, just to avoid wastage of time, I'm estimating the labels of this classifier only, the training labels, okay? And if you want to see the differences in the label, you should be able to see here, for example, all the A labels, because it has training error of 0, all the labels are correctly estimated. A means A. Correct label was A, estimated label is also A, right? But for the testing data, for example, now we are working on the testing data. So the same classifier on test set works like this. So if you see scatter test, I have plotted test data only, and on test data, I have plotted this classification. For this one, for example, I need to compute the testing accuracy now. For testing accuracy also, let's see for all of them, sorry. And 3C was the best classifier on training data, but on test data, let's see how much it gets. So 3C is still probably the second best classifier with 16% misclassification. So it means the accuracy is 84%. 84% of the samples were correctly classified, 16% samples they are mistakenly classified, misclassified, right? Now, again, if you see the labels here, you should be able to compare those labels, the estimated labels and the true labels. Label test, I did. Okay, I need to get these label tests here. So, yeah, so you see here, for example, this where I have pointed out, it was actually B, but it is now estimated as A. This is an error, okay? Also, like confusion matrix is also important. So we always plot confusion matrix to see how many false acceptance, false rejections are there. Anyone who has any problem in reading this confusion matrix? No? Okay, perfect. Okay, so for the testing data, this confusion metric of this classifier is this. So you see 43 samples of class A, they got correct. This diagonal means they are correct classifications. So 43 of them, they were correctly classified as A, 7 got rejected mistakenly, and 9 of class B, they were accepted mistakenly, false accept rate, and this is the true rejection rate. Okay. Also, like the ROC curves that I showed you, we also report somehow these ROC curves as well. So you see here, this is not ROC curves, I'm really sorry. These are DET curves because I wanted to show you false reject rate versus false accept rate. So these are DET curves. Also, I had to compute EER as well, equal error rate. So I plotted this. But if you just do this 1 minus false reject rate, it will be ROC curves. Okay, so here, for example, if you read this, 20 is the EER. So you see on X and Y, they are the same values. I don't know if it is readable. 20, it's written 0.20. So this was all binary class classification because binary class classifiers are robust. We all know they are robust because they just have to separate between the two classes. But problem is one class classification, you know. Now I'm deleting this data. I'm generating another data set. For example, here I have A, which is data, and for two classes, and I'm using one as the target class. So I said, if I'm Buriro, my target class is Buriro. Okay, so this is how it works. And B is the test data, which contains the data of Buriro, also data of others. So if you see this data, for example, you have this data, and if you want to plot, for example, a 2D plot, you should be able to see data like this. So this is the training data, okay, of only me. If you want to see the test data also, for example, you should be able to see here if you insert here B. So this is now test data. These blue lines, for example, blue samples, they belong to Buriro. Red samples, they are attacker samples. Okay, so now, for example, we need to train the classifiers. I have chosen KNNTD, for example, and as a classifier for one class classification. Let's see how it draws the boundary. Do you see the boundary? So if we, not on this, for example, if we train this on A and show it on the training data like this, for example, and we here plot this decision boundary. Yeah, this is how it looks like on the training data. Now, anything in between this boundary will be marked as correctly classified by that classifier because this classifier is being trained only on one class data. That is positive. Okay.
So is this the same classifier that you showed previously?
That was binary class version of it. Now this is a one class classification, one class classifier. So you see the difference. It has drawn a boundary only on one class data. There are no classes available here. So when we train this also, there is also a SVDD one class classifier. So SVDD draws a black line like this, for example, and anything in between this will be marked as the user A. So if here, for example, also you could plot the testing data, and on testing data, you could see, for example, like how it looks like. So again, the same concept, confusion matrix. If we need to plot the confusion matrix, now no need to plot the confusion matrix for training. We are directly plotting it for testing. So in the testing, you should be able to see this. For KNN, because it was the accurate classifier, 48 samples, they are correctly classified. Okay, only this one class training was done only on the user of one class only, A, let's say. Only one of his sample got rejected. 6 samples are mistakenly accepted, and 45 they are truly rejected. So confusion matrix is very, very clear. And if we want to plot now, for example, this ROC curve, we should be able to see this. So ROC curves is this, if you can read this. So this ROC curves now says, for example, here, if you are here, it means your X is 0.02. At the false classification of 2 means false accept rate. Outlier accepted means false accept rate. So false accept rate of 0.2, if you are agree, the true accept rate will be 0.88%, which is good. So here from the ROC curves, we also compare the performance of these classifiers. So here SVDD is not working at all. So this KNN classifier is good for me. I think the basics is now clear, right? Yes. So now let's jump into ClampOut. So for ClampOut, for example, the data that I am using now is the data that I showed you from the paper, okay? So first I would show you this data. And now, for example, for all 50 users, because in the paper they claim 51 users, but for one user, the data was missing, the file was not there. So we had to use 50 users data. And on different, for example, classifiers like 4 I have used. So you should be able to see now the process running. It will take like 2 minutes, for example, to compute for all 50 users. It is training of one class classifiers, testing one class classifiers, computing the confusion matrix, everything, ROC curves, everything. Any question? Yes.
I have one question. Depending on the number of the user on which you train the model, how common is to get collision, meaning that users are recognized as different users are recognized as the same one?
As the same user.
I imagine that more users you add to the system, more likely it is to happen.
It didn't happen. If you see the slide of scalability, it didn't happen actually. It didn't happen actually. It was because this data was collected in a very, very nice and controlled way, for example, and the data was so different from each person that it was classified very, very accurately. But this happens. I told you that there exists some sheep. This is Doddington Zoo. For example, I am a sheep. What does it mean by sheep? It means I have a lot of intra-class variations. Within myself, I cannot sign exactly the same way I used to sign 10 years ago now, for example. All my samples will be different. So if there are a lot of variations in my own samples, someone could exploit that variation and attack me. That category will be called wolves. I hope I answered you.
Yes, thank you.
48, 49, 49, 49, 49, 49, and 50, finally. Okay, so here, for example, now, these are the results that I showed you, but I didn't use LOFD at that time. LOFD, you see, this true acceptance rate is 83, averaged over all 50 users. True reject rate is just 16, which is 1 minus this true accept rate. False accept rate is 25, which is okay, keeping in mind that the data is limited, keeping in mind that we have not done any feature selection, we have not done any parameter optimization, like how many neighbors are we using, So it is a good start, right? Agree? Yes. So 87, with KNN we got 87, but false accept rate is a bit high, you see here, 35.53. 87 is good true accept rate, 12.98 is false reject rate, but still, we have to perform feature selection just to see. So for feature selection, you could try, for example, different approaches, but what I have done here, for example, these 8 or 9, you see EMG, CFS, no, sorry, these are for others. CFS, this one, CAE, attribute evaluator, GRAE, gain ratio attribute evaluator. These are different attribute evaluator that I have used, and using these as the schemes, I found these features. Okay, but it's not time to repeat them here. Now the point is, I'm stopping this one. I'm again clearing this one, and now I'm training these systems with the data that Kevin has collected now, just to show you how it works. For one class classification, for example, Mr. Kevin has collected data from 13 users. Now, if you could read this, we are using the data of 2 seconds here. Just 2 seconds. 2 seconds means like if the frequency of collecting data is 50 samples per second, it means you will have 100 values from each 2 seconds window. And here, so I read this data. It has 82 features. Okay. Yeah, sorry. He has managed to extract 82 features from each, and in 83rd feature there is a label. Okay, so but the users are just 13. I'm sorry to say, we have to increase this number. So for this 13 users, for example, if I run the same experiment and see how long it takes for 13 users. Already 11, 12, 13 done. So for 13 users, for device unlocking, one class classification scenario, we are reaching this with this LOFD classifier 94.10 true accept with all features. I'm not done any feature selection at the moment. And just 5% false reject rate, 26% false accept rate, and 73. These results are already good. We have to do this feature selection also. But the point is, more number of users, for example, would add a lot of value to this research. Okay, for KNN also, you see, they are 93%, so it is already very, very good. But we need to somehow address the problem of false accept rate. Okay. How many of you have used classification learner? You have used classification learner, very good. So at this moment, what I have shown you the results analysis of one class classification that I'm using, for example, for clapping, right? Now we are doing multi-class classification, replicating the scenario of accessing a building. Okay, so for example, I'm opening a new session here. I'm clearing everything. Okay, so here I'm reading that training file that I read. Here train. So classification learner here, it's asking me like if I use cross validation of 5-fold, for example, to get the training accuracy, for example, just to finalize the models, I'm using this. I could use hold on method or a resubstitution method as well, but I'm using this. So you took first 82 features as predictors, last column as your classes. Okay. So this is a multi-class classification problem. You see, you have 13 number of users and you have 82 features. Now, here you see also 82 features. For example, here I would like to use all the classifiers. So this tool, for example, is equipped with at least 44 classifiers. So idea is to, let's say, use all of them, for example, to train, and let's see what is the training accuracy. It will not take long, to be honest. Some of the classifiers, which are like ANN, for example, wide area ANN, or QDC, SVM, for example, it could take a bit longer, but I don't think they will take longer. So you see tree classifier already trained and got this validation accuracy of 84%. For a multi-class classification scenario. And this linear discriminant, you see 95.4. Kevin, you also have to note this. 95.4, this linear discriminant, probably because we have to implement this classifier to run on the server as well. Okay, and wow, you see SVM linear 96.9. SVM quadratic also 96.9. So the data set that Kevin has collected is better as compared to the data set that they collected in Wisdom Lab. So why I can comment that this data set is collected in a better way? Because This data set was collected in a controlled environment here in the university faculty building, and he was sitting in front of the participant, for example, to do this data collection himself. That's why. So you see here, if we count all the classifiers that are giving us more than 90% accuracy, how many of them? So there are like up to 2.31 classifiers. So you see here, 84, no, 1, 2.4 gives us more than 95 validation accuracy. Knife base 2, SVM linear 3, SVM quadratic 4, SVM cubic 5, medium Gaussian 6, Gaussian coarse 7, KNN 8, 9, 10 KNN cosine, 11, plenty of them. I've lost my patience to count. There are many. So the point is, if all of these classifiers, they are classifying these samples correctly, it means that classifiers are not overfitting. They are not biased, right? Now, for example, this was the validation accuracy. Let's try to test it on the unseen data, on the test data. So
sorry, before you proceed, this what about the quadratic?
Yes.
Discriminant thing. It failed. What's the?
Now, who would care? Just my point.
It's just good to know, like why.
We can see this why it failed. Probably because of the different, it will give you the error as well. One or more of the classes have singular covariance matrices for their predictor values. The makes training fail. We need to see this covariance structure. We need to seek the help. Just copying and pasting this error will probably solve this issue. But this is not the goal of this research. So at the moment, for example, now if you collect the test data, and your test data is in the workspace here, and I did this. So this was the validation accuracy. Now if we can test all, yes. Now the model was saved, trained model. Now we are testing it on the test data. The good thing of this tool is, for example, we can save that trained model somewhere, or we can save that entire training as a function to be called from other, yeah. This is very good point. So this tree has the test accuracy of 88.1, which is good. 88.1 also, 83, 30, linear discriminant analysis, 98.7, K1. So you could click this and see, for example, you got 95.4% validation accuracy previously on the training data, and now this test accuracy is 98.7. You could save this model and you could try, for example, using this model for testing in real time. And also, like here, the good thing is you could plot, for example, confusion metrics for this model. And so here, for example, on the x-axis, here, these are false rejections. You see 4 plus 2 plus 1. So 7 samples of this class, they got falsely rejected. And 2, 1, 3 plus 1, 4, 5, 7, 8. 8 of the 8 samples from other classifiers, they got mistakenly accepted as the same user. Yes. So this SVM, again, they are 98.8, 98.9, 98.9. Yeah. 97.7, 97. Neural network, this support vector machine, this KNN, all of them, they are performing well. So it means our data is good. We just need to have more data. Fine. Any question? Any question, Professor Hassan?
My questions.
Any question?
We already did a lot of questions.
Yeah, well, we were going while you are.
You are welcome. No, no question at all. So,
Maybe some future.
sure. Feel free to ask anytime. Feel free to ask. You can reach me on my email if, in case you are interested to conduct research in this domain, for example, take my help, for example. I would be very, very happy to collaborate. Now I would request you all, please, now that you know the importance of this work, the research that we are already getting, please contribute to this research and participate in the experiments. Then with 10 more users, probably we will be able to publish this work. Thank you so much. If you do not have any questions. Online participants, if you have any questions. No? Okay, good to go then.
Thank you.
I'm done, Professor.
Okay, thank you.